it's fine. It's good to know.
Didn't know it never should have been named.
Okay, so you're used to recording this.
What?
That's the end of this recording. They have a tiebreaker question on the Chem Olympiad exam, which is making tied. The test is 60 multiple choice questions with an additional 10 questions because our region is really competitive and like they need the extra questions to differentiate between people. But then there's also a written response tiebreaker question, which give me a moment. Let me get this up. Okay, so after the 70 really grueling, difficult multiple choice questions, you'll be given an essay question, where they will give you a scenario, and they will tell you to write about it, explain why this happened, talk about this, something like that. So the good news is they give us a clue as to what the question will be beforehand. It's still loading. Anyway. This year, the tiebreaker question is going to be about the Flint water crisis. I expect you're all at least familiar with what's going on, kind of. Alright, what do you guys know about it?
Lead and water.
Okay, yeah. Just say there's too much lead in the water. Beyond that.
Blood came from
Governments.
What?
Blood came from the pipes.
Okay. The lead isn't just showing up magically, it's coming from the pipe that the water's traveling in. Any ideas on why? Rick Snyder. There we go. That's going to be your turn.
Snyder for his pipes. Lead. Poison.
Okay, so, Andrew, can you pass my water bottle? Is this still recording? Darn it. I tried. Okay, so what the question will ask you about is the chemistry behind the Flint water crisis. So they'll expect that you know already that there's lead in Flint water. Chances are what they'll ask for is why. And also potentially what are some ways that the issue could have been avoided, how we can solve the issue, etc. So we don't know the exact question, so what I'm about to teach you might be on there, it might not be, it probably will be on there, but I apologize in advance, it was totally unrelated. Okay, so here's the idea. You have a pipe of water, right? So this right here is your pipe, your metal. It's going to be either lead or iron, and then you have your water going through it, right? Now this water can, or not the water, but stuff in the water can oxidize that metal, whether it be iron or lead, turning into iron or lead ions. So what they do in these pipes is that they have what they call a mineral passivation layer. And basically what that is, just like protection, right? What it will do is it will guard against stuff getting to the pipe. So you have your pipe, you've got the layer, and then you have the water flowing in the metal. So what they have is you have chlorine in your water for like antibacterial purification, whatever they call it, right? And it's supposed to be phosphate in the water to help out that layer. These are in very, very low quantities, but if this layer starts breaking down, then that chlorine and any oxygen gas you have in your water can actually start having an effect. So basically what happened in lead is that their pipes are really, really old. So this layer has already begun to break down. And what happens then is that your chlorine, the Cl2, will react with that lead, right? Making lead 2 plus and Fl-. Or similarly, oxygen gas within dissolved in the water can do something similar, and it'll make lead ions, which is the actual dangerous part in swimming water. It's not lead metal floating around, it's lead ions, which is the big deal. Because these pipes, which are made of lead, because they were made like, what, 100 years ago, have started to corrode and be broken down by stuff in the water because this layer right here is not as protective as it was before. Okay, so what is that layer? Well, like I said earlier, the layer is made of mainly phosphate, right? So the formula for phosphate is PO4, 3 minus. Are phosphate soluble? Usually. Yes? No?
No.
No! Phosphates are very, very infrequently soluble, only with like ammonium or sodium or something like that. So what will happen with the phosphate is that if this lead ends up, if the pipe lead turns into lead 2 plus, then that lead will react with the phosphate that's in the water and turn into lead phosphate, which is insoluble. What will happen is, in your pipe, you have your lead, right? Your pipe can turn into... So, we've got lead floating around. It comes across the phosphate. These will react and turn into that passivation layer. Does that make sense? What's going on? Kind of? Could you explain that on the test? If you were asked, what is the passivation layer? Or what protects the pipe? Could you explain what that is?
Okay, what's the actual layer made of? It's actually made of phosphate?
It's made of a lot of things. I'm not entirely sure like what the main thing is. But yeah, you do have phosphates in there. You've got carbonates, so like so phosphates one thing, carbonate will be another. That's all I know. Sorry. But yeah, phosphates, carbonates, other minerals. I think that's all you really need to know. I don't think you know much more detail than that.
Can I question you?
Okay.
So currently, there's a lack of phosphate, and it takes time for that to rebuild back up.
Right.
So as we've now treated the water, the pipe should be reforming this kind of insoluble protective layer slowly, and that's going to gradually decrease the lead levels back to where they were. The original problem was they had too much chloride, and not enough phosphate.
When they switched over, okay, so what Flint did a couple of years back is that they used to be on the Detroit City water line, and now they decided in order to cut costs, they're going to switch to another water line. And when they did that, what they were supposed to do was they were supposed to add phosphate to the water to prevent so if there is any lead in their pipes, it would precipitate and turn into the lead phosphate and everything would be good. They didn't. Flint forgot to add the phosphate, and okay, so like they didn't actually forget, but they decided that no, we don't need to add the phosphate. It's all good, and then eventually they're just like, oh crap, we should have added the phosphate. But at that point, it was too late for them to change it immediately. Like Mr. Malin said, now that they've added the phosphate, it'll take time for that layer to build back up. That's not done immediately. So this layer, at a point, would have been built up over years and years of constant phosphate-lead interactions, or whatever it's made of. Now that it's gone, it's going to take some time for it to build back. Does that make sense? Yeah.
Question, what would cause the mineral layer to actually corrode?
Just oxygen, stuff like that. There's one.
Salt oxygen.
Yeah.
Yeah, so you can do redox with that, and that's going to change your oxidation state. Yep.
What exactly, again, I'm not sure. I don't think you need to know. know that?
That's something too that takes time because you have very limited oxygen supply
Yeah.
in there, and so, and then that salt layer will protect against that.
That's what makes a salt corrode.
What makes the chloride corrode?
Not the passivation layer. The lead phosphate or whatever it is. No, it's actually a good question. I'm not entirely sure.
Not the metal, but the layer.
Right. If I had to guess, I would guess the chloride somehow interacts with it that makes it more soluble. Because everything I heard was that the chloride itself.
Okay, so there is one thing. Before I get to that, just one more thing about phosphates. So there are a bunch of different kinds of phosphates. Like what we think of as phosphate is just PO4 3 minus, right? That's what we learned. If we want phosphoric acid, we call that H3PO4. That's what we call orthophosphoric acid. That's like the fancy name for it. Then we can have a whole bunch of other stuff. We can have pyrophosphoric acid. We can have tripolyphosphoric acid, tetrapolyphosphoric acid, the idea is that there's a lot. But all that will work for the water, lead thing, that you want to add orthophosphate to the water. The rest of these don't work or they don't work as well. That orthophosphate is the one you really want. So if you throw that term out there, orthophosphate on the thing, I don't know, they might think it's great. Okay, so one thing that can make the layer break down is pH. So what they observed in Flint's water is that over time, their pH... What's the pH of water, or what should it be? 7-ish, right? Here in Michigan, we have a bit higher because of the Great Lakes calcium carbonate a little. Like if this is 7, Flint's water was like, I don't know, around 7.5, 8-ish before the crisis. And the thing is like, it was eventually started going down. I'm not sure why. Ideas?
The lead is one of those ions that will pull
pulls
complex
out, okay.
water and then cause it to release H+ ions. So the lead plus water will end up producing acid. Would be one of the ideas. Yeah. I don't know if there's anything else that would do that too. Was it really that exaggerated in the article? Like that big of a drop?
I think I said it went down to like 4.
Yeah. So 4 seems to me to be like a lead 4 plus, lead 2 plus kind of pH.
Okay.
So maybe that's it.
So, yeah, the pH of the water is going down. And what that'll do...
Oh, and iron.
Hmm?
Iron 3 would do that.
Yeah,
Yeah.
iron would probably be the bigger one.
Well, that's pretty acidic.
Did you guys learn that year 1?
No.
Yeah.
No.
You didn't?
They know complexes, but they don't know about the acid-base stuff.
Okay. So iron in water is acidic. Lead in water is acidic. So what those will do is it'll drop the pH down, and it'll make more H+ in the water. So you have your pipe, right? And you have your layer here, the passivation layer. So you've got like some phosphate compounds, you've got some carbonate compounds, whatever it might be. A low pH will increase the solubility of those. Can any of you explain why? Just went over this with you earlier today.
Well, it would react with it. Acid.
How?
It would take an H+, creating carbonic acid.
Okay, so if I have, let's say, lead carbonate here, right? PbCO3. That's going to react with an H+. So that carbonate especially will take the H pluses and turn into H2O and CO2, which will leave the lead, right, as ions in solution. So if I have high H+ concentration in the water, then these are going to react with the phosphate, carbonate, whatever else there might be in there, and that would be one of the things that would cause that layer to break down. So for example, if you have high concentration of iron in the water, or high concentration of lead, oh, it's really hard to see, sorry. Okay. that will cause H plus concentrations to increase because those are acidic. That they'll yeah, I'm not going to explain the concentration, whatever. And then that H plus will react with this stuff, causing the layer to break down and then expose the pipe underneath. Okay, does that make sense?
Mm-hmm. Yeah. Where's the iron coming from?
Iron?
Pipes.
Yeah.
So it's made of iron and lead?
Some pipes
So
are-
all
some
this
pipes-
water is going to flow through like a whole series of pipes. I mean, a lot of the people who live in Flint have PVC piping in their house, but they're still going to have elevated lead levels from somewhere along the line. And even if it's not directly, like, yeah.
It's like, yeah, all these pipes are like really, really old. By really, really old, I mean like at least 50 to 100 years old. Like these were some of the original pipes that were being laid down when like, you know, indoor plumbing became a thing. So in a lot of those pipes already, like it might have been before the whole orthophosphate treatment was invented or whatever it might be. But a lot of them were already very worn down. And so that's causing the high lead concentration in the water, or sorry, high iron, which in the lead pipes is causing high lead, which is the real big problem. Right? Like iron is bad, but not nearly as bad as lead. Does that make sense? Yes? Okay. That's kind of the gist of it. Ways to solve it, or like treat the, you know, treatments that can be done. Adding orthophosphate is something that they've been doing, trying to, you know, make up for screwing up. But it'll take time. Raising the pH again by adding carbonates and such, again, also will take time. Anything else?
More than I know.
Okay.
Thanks. My turn?
I have pictures though.
Oh, I'm sorry. I thought you were done.
Okay.
Looks like applesauce.
It does look like applesauce.
You want to drink it?
Yeah.
This would be like very iron-y water. The reddish orange color indicates there's a lot of iron in there. Then, oh, so here's the pH over time. Okay, here's one I really wanted to get to. Here are the pipes. Oh, come on. Guest Wi-Fi.
You're on guest?
Yeah, what else would I be on?
Sad.
Devices.
Only way to go.
If you want to give me the
Here,
password,
give
I'm open
us.
to
Where's
it.
Carlisle? She said she wouldn't.
Carlo gave you this thing?
No, she said she wouldn't.
Oh.
No. We had a freshman year.
Yeah,
Remember that?
the corrosion of the
Wasn't it
pipes.
like nose? Yeah,
Oh.
no students or something.
So this is all iron. I think both of these are lead, or they might all be iron. Yeah, different types of iron corrosion. So that's what happens when that layer breaks down.
Like in B-Pod.
Like in big bud.
You all know. You all know.
All right, any questions? Sorry, my presentation kind of bad. I kind of made it up earlier today. Okay, so if you were asked to explain what's going on, could you do it?
Partially.
Like, they'll have like a couple of sub questions, like, it won't just be one long essay, it'll be a couple of short responses, like, okay, well, what happened? Like, what was the big deal? Or, what is being done to solve it, etc. And for the most part, like, if you have a general idea of it, that stuff in the water, like oxygen, chlorine, will turn the the metal, either lead or iron, into the ion, then yeah, you're good.
In high school.
Good?
Cool.